Welcome to our webcast, Integrating Wireless into an Industrial Ethernet Application. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. In this RCEP webcast, you will have the opportunity to learn about wireless selection criteria, including equipment reliability and capabilities, availability, ease of management, conformance to open standards, and integration with an existing Ethernet network, along with key trends in wireless and Ethernet based on Control Engineering research. A question and answer session will follow as part of the 1-hour webcast. Now we have the speakers for today's presentation. Dan Capano has more than 30 years of experience providing instrumentation and electrical consulting work and services to municipalities and clients in the private sector. Dan has been published extensively, including a textbook, Network Cabling for Contractors, in 2000, and contributed to the Instrument Engineer's Handbook, providing chapters detailing the use of proprietary data buses and wireless network technology. Capano is the owner and president of Diversified Technical Services of Stamford, Connecticut, providing technical services and staffing to the water treatment industry since 1997. He also serves as the president of the New York section of ISA and vice chair of the Stamford Water Pollution Authority. He is a certified wireless network administrator. I'm Mark Hosky, webcast moderator and content manager for Control Engineering since 1994. Before we continue, please consult this summary slide to see how to deal with technical questions. In November 2014, Control Engineering conducted research on mobility, Ethernet, and wireless. Results here are based on replies from 290 respondents, and the last survey response was taken at the end of December 2014. I'll review some of the Ethernet and wireless results in the next few slides. Control Engineering identified the following trends about product spending, integration, and challenges for the use of Ethernet and wireless technologies and how they help users of automation controls and instrumentation to be more productive. These technologies are key to components and plant-to-enterprise integration, industrial Ethernet, Internet of Things, and big data analytics and optimization. I'll go over these summary points in individual slides now. Most popular Ethernet products for those who use, buy, specify, or are expected to specify in the next 12 months were Ethernet switches, Ethernet wire or cable, Ethernet networks, Ethernet routers, and then Ethernet connectors, gateways, cord sets, and other Ethernet infrastructure hardware. About half the respondents will spend more on Ethernet products in the coming year. 41% will spend about the same. As for Ethernet integration with automation, controls, and instrumentation, 29% said they were highly integrated in their installations, and 49% said somewhat integrated. Among the challenges when implementing Ethernet security topped the list, and it's a much greater concern among these respondents than respondents to the survey a year before. You can see some of the other concerns in the graphic there. On the wireless side, the most popular wireless products for those who use, buy, or expected to specify in the next 12 months were wireless routers, antenna, and gateways. These three were all over 50%. Note the 30 percentage point increase in routers year over year. More respondents expected to increase spending for wireless, 60% in total. 1/3 will spend about the same. 44% of respondents reported their controls, automation, and instrumentation are somewhat integrated with wireless technology. Just 9% said they were highly integrated. For those that have attempted to integrate these technologies recently, 58% found the process somewhat challenging. Among challenges when implementing wireless technologies, security also topped the list, with about the same level of concern as the last survey. Security issues were 50%, lack of training, education, processes 31%, and lack of knowledge or use cases of benefit were 38%. Those were the biggest issues in adoption of wireless technologies, as indicated by the 2014 survey respondents. So in summary, control engineering research on Ethernet identified switches, wire or cable, networks, and routers as the most popular products. 90% said they'd spend more or the same in the coming year, and 29% said Ethernet is highly integrated with controls and automation and instrumentation. 45% said security is the largest challenge with Ethernet. With wireless, the most popular products are routers, gateways, antenna, modules, and receivers. 93% will spend the more or the same in the coming year. Just 9% have wireless that are highly integrated with controls, automation, and instrumentation, and half said security is the largest challenge they have with wireless. And now, on to Dan's presentation. Dan?
Thank you, Mark, and thank you to everybody who tuned in. What we're going to be talking about today is a proof of concept project we did at the Stamford Water Pollution Control Plant. The first slide shows the layout of the plant. Just to give you some rough dimensions, the short axis is about 800 feet side to side. The long axis is 1,200 feet. We're surrounded by businesses and industry, so that was a concern when we avoid the wireless. Just some facts about the SWPCA, located in Stamford, Connecticut. The plant is rated at 24 million gallons per day. We're currently undergoing a $47 million 5-year systems upgrade, and this includes a new SCADA system. During the planning phase for the SCADA system, it was decided that we would explore other means of connecting the sensor network in the plant and try to reduce our use of low voltage wiring by using wireless. And I will tip my hat to the board. They are very, very proactive in reducing costs. Very successful, as a matter of fact. So kudos to them. The SCADA upgrade is going to be replacing an obsolete SCADA system that was installed back in 2007. It will involve new DCUs upgraded with new PLCs, existing fiber optic local in the plant we'll be using. And the wireless system will connect to and augment that existing Ethernet fiber optic LAN. And we plan on using wireless for future process instrumentation expansion, and that will avoid quite a bit of cost in wiring the sensors. So using a IEEE 11 wireless for replacement of low voltage signal wiring was very appealing to us because wireless is much less expensive and much easier to install than wiring. And wireless can be used for other tasks besides instrumentation and control systems, such as voice over Ethernet, asset tracking, as you can see, CMMS integration, and several other uses, which will be other slides. Mobile process monitoring is becoming an eventuality. It is an eventuality. And during the planning process for the new SCADA system, the staff has stepped up and actually asked for it. They want to be able to see the process, if not control aspects of the process, using a mobile device wirelessly. So getting into the POC, we wanted to use wireless and instrumentation vendors that we knew that were reliable, we knew their capabilities, that would provide availability of the network and the subnetworks, ease of management, and most importantly, conformance to open standards so that we could have commonality of equipment and we wouldn't have to do too much in the way of protocol translation. So the proof of concept was done for several reasons other than what I've just explained. The wastewater industry, the water industry, is very slow to adopt wireless technology. There's a lot of reasons for this. One of the reasons is that the environment is corrosive and toxic, and the equipment available, wireless equipment available, was not such construction at that point. In other words, the enclosures would not stand up to the abuse. So we wanted to do this using equipment, newer equipment that would demonstrate the use of the technology and which would also save the authority capital expense in the future. So, and also to expose the staff to wireless. We gave staff access to the wireless network in order to get them used to using it, and it has been quite a success, and I'll go into that in detail a little bit later. We wanted to flatten the network. We didn't want to have a hierarchical system of networks layered on top of other networks. We wanted to have a flat network throughout so that anyone on any network segment could access process data. And obviously, cost, a major factor in municipal environments and decision making. So wireless will reduce the repair, maintenance, and replacement costs associated with hard wiring. We selected the primary odor control system for the proof of concept for a couple of reasons, a few reasons. First, it's a convenient 330 feet from the control room, which many of you will recognize as being a maximum Ethernet or wired Ethernet segment without the use of repeaters. So we can do an apples-to-apples comparison. The odor control system is a slow and non-critical process, so we didn't have to worry about taking down a critical process if we did lose the network for any reason. The several parameters we selected, sump level, bed DP, pH or P, and blower vibration were typical values that are monitored on an OCS. The propagation path between the odor control system and the control room lies pretty much along the short axis of the plant. So it gave us a good sense for the coverage along the long axis of the plant. And so it was ideal for the demonstration of Wi-Fi coverage and the backhaul performance. This is a picture of the odor control system. It was actually designed as a two-stage. We converted it over to a single stage. It works very well. The neighbors are very happy. For process wonks, this is the P&I drawing for the primary odor control system. Oops, sorry about that. So now let's get down to what was one of the primary drivers. We wanted to come up with a long-term solution, a long-term low-cost solution, and that brought into play a lot of different factors, not the least of which was the installation cost. And as you can see, there's quite a difference. For a 300-foot wired link in a trench, which had to go beneath various surfaces, landscaped lawns, parking lots, and sidewalks, you can see that the cost for that was $30,200, and that's a conservative figure. On the other hand, putting up a wireless link across the same distance was $5,420, or roughly 75% less. So this this got a lot of attention, and everybody, I mean, that was the first question that was asked, was how much will it cost? So the board was favorably impressed and gave us permission to implement this proof of concept. The basic concept was to take the primary sensors and using the 2.4 gigahertz local link, which is on the industrial, scientific, and medical band. It's an unlicensed band, and communicate directly with the IEEE 802.11 Wi-Fi access point mounted on the odor control system tower. The other access point is mounted on the control room outside wall and then networked into the operator workstation in the control room. Between those two, 30 feet, we use the 5 gigahertz channel to accomplish a wireless backhaul to replace the wired. The 5 gigahertz channel is in the unlicensed National Information Infrastructure Band, or UNI-band. It's a very quiet band in an RF sense, and we felt that that was our best option. In fact, we consider that our best practice is to do local connectivity at the 2.4 gigahertz band and do wireless backhaul or point-to-point bridging using the 5 gigahertz band. So the first step in putting this together was to do a site survey. So the first thing we did was plug in all the values into a program to do a predictive site survey. And you can see the results of that here. The orange and yellow circle at the lower right is the location of the odor control system. The other AP at the upper left, the relative upper left, where the orange is the control building. The propagation strength varies from red and orange being the strongest to blue being the lowest. You can see that a substantial amount of the plant is covered using just 2 APs. They are running at about 100 milliwatts, 20 dBm. The coverage is actually much better than shown. It did meet and exceed this predictive drawing. We did a manual survey following, and we found that along the top of the drawing, there was a pretty good coverage, and it dropped off very conveniently at the fence line, which was good because we didn't want to disturb the businesses or have them intercept our network. Okay. So just to go back over what our design criteria was, we wanted to use a dual band access point, wireless access point, using the 2.4 ISM and 5 gigahertz UNI bands. The instruments were to operate on the ISM band, but we found that the only instruments available did not operate using the same modulation technique as Wi-Fi. The instruments use wireless HART, which is wireless highway addressable remote transducer, an old wireline instrument diagnostic tool and reporting tool, which has been adopted for wireless. But that system uses frequency hopping spread spectrum, which utilizes a modulation technique where the transmitter hops from center frequency to center frequency, versus the 802.11 Wi-Fi, which uses OFDM, orthogonal frequency division multiplexing. So there had to be a way to convert the primary sensor data to Wi-Fi. So as you see, the instruments will talk to a local 802.15.4 gateway. 802.15.4 is a personal area network, IEEE standard. You probably recognize it as Bluetooth. which uses the same basic modulation technique. The gateway is then networked into an 802.11 industrial access point. We call this a translational bridge because basically what it did was translate from 802.15.4 to 802.11n. Then that bridge would then communicate with the local 802.11 mesh point, which would then communicate with the control building using the 5 gigahertz channel as a wireless backhaul. So just a little bit more about 802.11 versus 802.15.4. 802.11, I think we can all agree, is the de facto wireless standard for wireless LANs. 802.15.4 defines personal area networks such as Bluetooth and wireless HART. As I mentioned, 802.11 uses OFDM, where 802.15.4 uses frequency hopping spread spectrum modulation. Again, wireless HART was chosen for primary sensors for convenience, and 802.11ap was chosen for Wi-Fi connectivity. Just a few words about an idealized plant network. We believe that an ideal network is a hybrid of wired or fiber and wireless. And of course, the network should be secure and fast. Fiber optic has certain capabilities, inherent capabilities, such as being physically secure in the sense that it really is not easily hacked into. You can easily hack into a copper network more easily than you can with any other. And it's very durable. It is not really affected by toxic and corrosive gases that you would find in a wastewater treatment plant environment. Fiber also offers a very wide bandwidth and minimal attenuation, which really is an enhancement to the wireless network. We wanted to have redundant mesh portals. This is a mesh network, a mesh wireless network. So an ideal network will have more than one mesh portal. A mesh portal is an AP, a wireless AP that bridges the wireless side of the network to the wired or fiber side, so you can get access to the wired network resources. And we chose mesh architecture because it was very robust. It self-forms and self-heals. If in a properly designed wireless mesh network, you could lose an AP without really having a detrimental effect on the overall network function. In the final implementation, we'll be using directional antennas to minimize spillover into the neighbors' networks and minimize the opportunities for eavesdropping. So here's just a depiction of what a mesh network could look like with process control panels connected both to the wireless network and to the fiber optic LAN. Another factor that was discussed and considered is that wireless mesh architecture is very well suited for distributed control systems. The underlying principle of DCS is that the loss of a node or of the network itself will not interrupt the function of an individual process or even of the entire process. So between the mesh architecture and DCS topology, there is really no single point of failure. So it's very robust, and they complement each other. As we mentioned, the mesh architecture is redundant and robust. It will self-form the network, and it will self-heal on the loss of an AP. And jumping ahead, wireless can be used as a primary or secondary network. This probably will become more prevalent as time goes on, and the utility of a wireless network is realized. The other thing I want to point out to everybody is that treatment plant topography is ideal for RF propagation. Typically, treatment plants are located away from population centers and the RF congestion that goes with it. So you have a relatively quiet RF environment within the fence line. You also have large flat tanks and elevated structures surrounding them. So you couldn't ask for a better setup for placing wireless APs and wireless instruments at field locations. Most of the instruments will have an RF line of sight with a properly placed AP. And power for the instruments and for the APs is usually available mostly anywhere using lighting or utility circuits. Now, wireless security was something that came up. That was the other question. What does it cost? And is hack into the plant network and shut off pumps or dump chemicals? So these are pretty unfounded. I mean, using good passwords, just typical 8 or character passwords, would take someone probably somewhere between 15 and 20 years to crack with a brute force attack. But no one really is going to take the time because there are other targets of higher value. Usually a wastewater plant is not producing anything of great value. The access points we're using also have the capability of a private BSK appreciate key. That says preset, but it's actually pre-shared. And basically what that means is a password or passphrase, which means that if each individual using the network has its own passphrase, then if they are compromised in any way, then only their passphrase and not everybody else's has to be changed. We also limited using the transmitter power control. We limited the propagation to the plant footprint to avoid interference with neighboring networks. You don't want to get complaints from the neighbors that we're stepping all over their network, and also that will reduce opportunities for anybody who's eavesdropping. Finally, when we do full implementation, we will hide the network name, the SSID, the surface set identifier, so that a determined hacker can find it, but for the most part, the casual eavesdropper will not. One thing that should be realized, a general rule of thumb is that a slower process uses the lower bandwidth. The slower a process changes, the less sampling you have to do to monitor that change, and therefore the less data you're going to generate. So the less data you have to transport. So we're using, for this particular application, we're using a fraction of the available bandwidth. It's 802.11n, so with the available equipment and technology, we can achieve an aggregate throughput of about 650 megabit per second. We're using a fraction of that. So using the excess bandwidth for video and voice will allow them to operate without experiencing too much latency. They are very latency sensitive, voice especially. So we're looking into doing voice over IP for intra-plant communication, video security monitoring, and in the future some asset tracking. Also mobile worker, which many of you are familiar with. As we spoke of before, the staff would like to monitor and control their process from anywhere in the plant using a wireless mobile device. And that will be very possible. We will have adequate bandwidth for several users to do that. Installation was also a big money saver. We were able to get the entire network up and operating within 2 days. The bridge, the translational bridge, was a bit of a challenge, and that required some development offline. But once we had that figured out, the entire installation was up and operating by the end of the second day. And it was easily integrated into the existing control room LAN using a simple switch. The configuration of the network is done on the cloud. It's a cloud-based utility. And what was really very impressive was when we powered up the mesh portal at the control room and then powered up the mesh point out in the field, the network automatically configured, recognized each other, began to exchange data immediately. So the comparative installation and downtime of the two systems, again, wired LAN installation, not only costly, but 2 to 3 weeks to operational, depending on a lot of factors, weather, availability, personnel. Wireless LAN, 1 to 2 days for a comparable link. So you could work between the raindrops if you had to. Wired LAN downtime could be several days to several weeks. The backhoe syndrome is very common, as many of you know. There's just so many things that can happen to wired systems, and it takes a long time to get them back up and operating satisfactorily. Wireless downtime, you lose an AP, you replace an AP. If you have one in stock, that is, even if you don't, you could have it overnighted and be back in business the next day. But on a properly designed network, you probably won't even miss the AP. So the final as-built configuration, as you can see, we added the bridge. So the 802.15.4 2.4 gigahertz band communication exists between the primary sensors and the bridge. And then between the bridge and the Wi-Fi mesh point at the OCS, it was done over the 2.4 Wi-Fi link, 2.4 gigahertz Wi-Fi link. And the rest is the same. We communicated using a 5 gigahertz channel backhaul to the control building. Compare that to the original concept. As you can see, we use the bridge finally, and then we have this is the bridge block diagram. You can see on the left communication with field devices using 802.15.4, and goes into the gateway. Within the gateway, we had a small 802.3, otherwise known as Ethernet LAN, connecting to an 802.11n industrial access point, which then communicated with the local 802.11 mesh point. There are devices out there since this proof of concept which do it all in one box without having to put it together yourself. Just a couple of pictures. Clockwise from the left, upper left, that gray box contains the 802.15.4 gateway and the 802.11 hotspot or access point. You can see the mesh access point and the PoE injector, the power over Ethernet injector, mounted on the light pole. The access point on the control room is shown at the lower left, and with a single cable coming through the wall that both powers the access point and provides data, two-way data. This is two of the field sensors. These are two of the field sensors. The one on the left is a sub-level pressure device with the transceiver is connected to the left-hand side of the T conduit. On the right-hand side, you see a typical instrument. I'm sure many recognize it. That is not really connected to anything. We put it in to test the local mesh. What I forgot to mention was the sensor network, the Y-Heart network, also forms a mesh network. So if you have something that's blocked, say, with a large metal pipe or wall or some device that inserts attenuation, then using a properly placed Y-Heart device will allow a path, an RF path, back to the gateway. Now, this is something I alluded to earlier. The plant staff originally resisted the idea of having a wireless network. And I have to say, unfortunately, that was among some of the older operators who had been there for years. I can't repeat what they said about the wireless system. This is a family show. The younger operators requested access to the network almost immediately once they knew it existed. So what we did was give a couple of operators access rights to the network and ask them to break it. In essence, run it through its paces, do as much as you can with it. And they did. They were able to access their the internet, their email, and also instructional video from vendor sites. And they reported that the coverage was solid, did not lose over 60% of the plant area, and the video quality was very good, very solid. No jittering, no latency, no buffering. And last but not least, it was that they were able to access the process data from the odor control system on their smartphone or their tablet from within the coverage area of just 2 access points. So we were very, very impressed by this test. And one thing I did forget to mention was that this test happened over a period of about 9 or 10 months, starting in April of 2014. The system is still there in operation, still operating very well, and we are making plans to integrate 2 or 3 more access points into the new SCADA design, which we believe will give us adequate coverage over 100% of the area, of the plant area, process area. So finally, just to do a quick comparison between wires and wireless, we've established that wiring is very expensive as compared to wireless. Wireless is a very inexpensive option to low voltage wiring. Wiring is very labor intensive. In this environment, everything has to be NEMA 4 or 7 rated, which requires conduit and enclosures that conform to those 2 standards, which, as you well know, can be very expensive and again, labor intensive to install. Wireless, as we said, these things are just installed up on a pole. The APs that you saw were IP68 rated. They've gone through this past brutal winter we had and haven't experienced any problems whatsoever. Wiring typically takes a whole lot more time than wireless, just for the reasons I just explained. Wiring suffers from long-term deterioration. Anyone out there who has done upgrades to water or wastewater treatment plants knows what I'm talking about. Metal rots. Gas finds its way into junction boxes and conduits and eventually destroys the copper or destroys the conduit. There is really nothing on a wireless system to deteriorate. So that problem goes away for long-term maintenance. And wiring, I'll make the point that even if we were to put a pipe and wire between the control room and the OCS, you would get a single link between the control room network and the OCS. And you could do what you want with it, of course, at either end, but with the wireless system, we're getting coverage over 60% of the plant area and also monitoring OCS parameters. So we're very, very happy with the performance. It has the wireless system has met and exceeded all of our expectations, and we consider it an unparalleled success. So I want to thank you all very much for listening to me drone on about this project. You can find a complete write-up in February's issue of Control Engineering magazine. And again, thank you very much. Mark, I turn it back over to you.
Thanks, Dan. As mentioned, the webcast participants can find more about the application in the February cover story, also online at www.controleng.com. Now we'll get on to a few audience questions. Dan, you can go ahead and use the interface and prioritize there as we discussed, and I'll explain to the audience how this works. Say, even if you're listening to the archive, hang on for these questions because it's always fun and informative to get to what's on listeners' minds. So the audience listening live can type questions in for today's presenter in the Ask a Question box on the screen, and we'll get to as many questions as we can. Within a few days, the presentation will be available for on-demand viewing, and we'll post the archive on the Control Engineering website and then send all the registrants an email message with a link connecting directly to it and related resources after it's ready. We'll link to the cover story. We'll link to some wireless tutorials. It'll be a great resource. And for those of you listening to the archive, do stick around for a few minutes because the Q&A is fun, and we'll try to extend it to the top of the hour. Now on to the questions. So here's Dan's contact information and two of the links to more resources. You can get a hold of me through the website. Let's see. First question, can conversion to wireless be done piecemeal, and can nodes on a local area network be made wireless?
Sure. If you have a wireless system in place, you can easily expand that by adding more access points, and you can bring instruments on as you need them, and simply just associate the new wireless instrument to the wireless network. Of course, I mean, you have to plan out the wireless network so that you have adequate coverage, because it won't do you any good if the instrument can't talk to the access point. But yeah, that's how a lot of plants are doing it. They are converting to wireless on an as-needed basis. As say a low voltage wiring system starts to fail, they'll replace it with a wireless link, and it's very easily done. Good.
Here's another question. It simply says BYOD. We know that means bring your own device. For the plant operators, were there any specific instructions or guidelines on working with their own devices?
Well, yes. Actually, the system is designed to be open. This is why some of the criteria we used was one of the criteria we used in selecting equipment was that it had to conform to open standards. So the standard that we used was the de facto wireless LAN standard, IEEE 802.11n, and any device that conforms to 802.11. 802.11n is backwards compatible to both B and G. A, B, and G amendments, which are older and slower. But we planned to incorporate as many mobile devices as possible. Remember, we're in a closed facility. We have a limited number of employees. and staff so that we can control how many people are on. What we did ask was that they choose strong passwords, 8 or 10 characters at least, and using special characters and capitals, and not to abuse it. And that's as far as I'll go on that score.
Good. And for work purposes, Dan, what kinds of things are they looking at?
They are, what they can do, what we've told them they can do is if, for instance, you're at a pump or an instrument, then you need to make an adjustment, or you need to tweak or calibrate. You could easily go on to a vendor website, pull up the manual for that piece of equipment, or even calibration instructions, or even in extreme cases, or even in routine cases, you could contact the vendors through the chat window that many of them have and ask questions right there on the spot. This is going to really drastically increase efficiency and reduce lost time costs by allowing the staff member to get a lot more information right there at the equipment location instead of having to walk all the way back to his office and use the phone or go sifting through files. So this is the kind of stuff that we've tried to educate them to use. So this is why we did not restrict their access to the Internet, because there's so much information out there. And in the future, we will have surveillance of the equipment through either wireless or wired cameras, and of course, access to SCADA. So you'll be able to bring up all the SCADA screens as you walk around the plant. If you're on one side of the plant, you could look at the process happening on the other side of the plant. If you want to make an adjustment, you could do that pretty much wherever you want. So that's how we're trying to push that exposure, so that not only is the staff getting more comfortable with it, but they start to learn its capabilities and utility.
Good. A couple of questions rolled into the next one. Reliability and ease of operator maintenance, compatibility with other systems, and use around airports or military bases.
Okay, that's a lot of question. The system is very robust and reliable as a result of our pre-deployment RF surveys, and with the use of the mesh topology, it's a very robust system. We believe that this is probably the most reliable configuration that we could put together. The system was very easily integrated into the existing fiber optic LAN. And it should be noted, well, that's an interesting question about use around airports and military bases. The Uni 2 band, which runs from about 5.25 gigahertz through 5.7 gigahertz, somewhere in that neck of the woods, that's shared with the approach and Doppler radar systems. So those two bands, well, that's actually Uni 2 and Uni 2E, which are what they call the lower middle and upper middle bands of the Uni band. They are required to have transmission power control and dynamic frequency selection. So any devices that operate in those two bands have to listen to see whether or not a radar or other military system or airport system is transmitting, and then switch to another frequency in order to avoid any interference with those systems.
Great, thanks. What's the best strategy for OT Wi-Fi that lives in the same space as IT Wi-Fi? So,
I'm thinking OT stands for operational.
Right, operations versus IT.
Right. Okay. Well, the systems can usually coexist. If you use a multi-channel architecture, usually, as I said, the bandwidth is adequate. because the processors you're going to monitor are very low bandwidth. They don't use a lot of bandwidth because they're very slow. They don't change very quickly. So you do have a lot of space, a lot of elbow room, let's put it, for a lot of different uses. Again, it goes back to the whole concept of flattening the network. Being able to use it for multi-purpose instead of just having, you'd have an office network and then a process network. I mean, this can all be combined into one, and security can be accomplished through the system of permissions that is already used. So I don't see any issue there as long as the system is designed properly. And then there's also the use of VLANs. You can VLAN the wireless segment. You could VLAN the office segment. You could VLAN any other segment and segregate traffic that way.
Good. So make various segments modular networks within the whole, right?
Right. Well, that's the purpose of the virtual LAN, the VLAN, is that you can segregate traffic that way. And some wireless APs have the capability to segregate traffic wirelessly. VLANs are common wired technique, but as I said, some wireless vendors, not all, have that capability.
How about interference within plants or facilities or manufacturing areas? How can the reliability of Ethernet radios be improved when working around variable frequency drives, for instance?
Okay, well, here's one of my favorite subjects. VFDs are notoriously noisy. They throw out so much electromagnetic interference that I believe the best practice is to segregate them, put them in a shielded room. I have seen not only for wireless but also for wired systems, VFDs can and will corrupt the signals. I've seen installations where just a simple Modbus network cable is run through a VFD room in a conduit, a metallic conduit, and the signals were completely unusable.
So segregation and shielding are best.
Segregation and shielding, absolutely.
Good. And what's the best way to educate others on integrating systems?
Well, what we're running into, and that's, again, I alluded to this early on, is that our industry seems to be very slow in integrating wireless into the process networks, because I do believe that not a lot is known about wireless networks, and no one wants to be the first. And that was one of the reasons why we did this in Stamford, was to show that it was viable. So the best way to educate others is to show the utility, to listen to webcasts such as these, to read. There are several trade groups that provide certification, and the study guides are excellent sources of information on wireless technology, and of course the Internet, and Control Engineering Magazine, of course.
Oh, well, thank you, Dan. Appreciate it. So thank you, everybody, for all the questions. There's a lot of great information here, and Dan agreed to answer some of the unanswered questions in print. He's going to type up the answers, and we'll make that available on the webcast archive. So look back there for any questions that you asked that didn't get answered, and we'll do the best we can to provide you answers. We'll also link to additional resources. Thanks very much, Dan, for great speaking and sharing the time expertise with this application. We'll link to the tutorial blog, the cover story as mentioned.